Hi, my name is Alyssa Murphy, and this is my video lab report for Lab 2, Motion of a Falling Object for Physics 2211, Section W02. So starting off with a brief introduction, the purpose of this lab was to show that there are forces other than gravity present during freefall. In the case of this lab, we'll be talking about the drag force. So the concepts that we'll be going over are the momentum principle, Newton's second law, and then we'll be talking about gravitation, and then how drag force makes the force in a free fall a non-constant force, and we'll be using some computational models to show that. So the equations that are used, the drag force equation is B, which is the coefficient, times the velocity, the magnitude of velocity squared times negative j hat, and then the gravitational force is, as it usually is, negative mg times delta hat, or j hat, and then for momentum, we'll be using position update, which is RF equals RI plus V average times delta T. And then for velocity update, we'll be using VF equals VI plus F net over M times delta T. So then for a preview of the results, after both computational models were created, the one that included the drag force in the calculations was more accurate to the experimental video, and this could be seen when graphs of position versus time were compared. So for the experimental model, the system was a crumpled up paper ball. The surroundings were earth and the air, and then the initial conditions, I made sure that the tracking with tracker began only once the ball actually started falling. So then here is the tracker video, slowed down slightly. And then for the computational models, starting off with model 1, the purpose of this model is to show just gravity acting on the ball, not including any drag force. So what I did for this model was I changed ball.m to be the actual mass of the paper ball, which was 0.005 kilograms. And then I set the initial position to the tracker initial position of negative 0.0298 meters. And then I changed the initial velocity to the 0 vector as it is in free fall. And then delta t was changed to be more similar to the tracker time frames, and b stays at 0 because drag force is not considered in this model. And then for the loop, I set the time in loop to the total time in the tracker video, which was 0.633 seconds. And then I changed f net to be the force due to gravity, negative mg, in the direction of j hat. And then for velocity update, I set that equal to f net over m times delta t, which is seen in the momentum principle. And then position update assumes that the average velocity is the final velocity calculated above. And then nothing else for the rest of this change for this model. So then here are the graphs created. The position versus time graph is the correct shape. However, it travels slightly further than the tracker video does. The tracker video ends about right up here. And then because gravity is the only force considered and it's constant, the velocity versus time graph is linear. So then, moving on to the creation of Model 2, which accounts for the drag force, everything is exactly the same in the first part of this, except the value of B has been changed to reflect the drag force. The new value is 0.00432, and this was determined by checking many different B values and comparing the resulting graph to the tracker data. So then for the loop, F net now needs to include the drag force, which is Fd, which is calculating negative b times the speed squared in the opposite direction, so negative j hat. Velocity and position updates remain unchanged, and then at the bottom, these arrows were created to show the drag force and the gravitational force, and then that's shown in the next slide. So here are the graphs. Position versus time now more accurately represents the tracker data, ending at around negative 1.5 meters, and then velocity versus time is now nonlinear, showcasing that there's a change in force present. And then this graph on the right, these vector arrows show the drag force in the opposite direction from the gravitational force. So here's our comparison graph. The orange line is the tracker data, the gray line is the with drag data, the blue line is without the drag. And so these models, the model that includes drag is more accurate to the experiment than the model without drag, which we can see here. However, there are some inconsistencies between the tracker and Model 2. So for possible errors, for tracker video, the tracking did not start at exactly 0, which could lead to some time inconsistencies, and the axes did not line up exactly with the movement of the paper, so it's possible that the position values were slightly incorrect. And then for the drag force calculation, there's some errors there possible. The B value, the coefficient, was found by checking it with the tracker video, not officially calculating it, so it was probably slightly incorrect, which may have caused those slight discrepancies in the graphs. So for the what does it mean question, we're asked to consider if either of the models predict the terminal velocity. So on the left we have Model 1, on the right we have Model 2. Model 2 does predict the terminal velocity, as we see at the bottom here, where it starts to reach this kind of limit of around negative 3.25. So this would be the terminal velocity for the paper ball in this experiment. And the what if question asks us to consider what the terminal velocity would be if the object was initially thrown down. So in GlowScript, I changed the ball velocity to be 0, negative 1, 0 instead of 0, 0, 0. The terminal velocity is the same, however the object reaches it faster when the object is thrown down. Thank you very much.